In this video, we'll be looking at some of the ways that proportion is applied to different areas of maths. We'll be looking at how to use a proportional multiplier or scale factor to change the size of shapes and quantities. We'll also make sure to be using the correct units of measurement in all of our calculations. Before starting this video, make sure you've watched the video on ratio foundations and transformations, especially the enlargement section, as several ideas used in that video are continued and expanded in this one. In this first example, we have a very common question that uses proportion. We've got a recipe question in which we're being asked how much of each ingredient we will require to make 30 cupcakes. We could simply scale it up by making a batch of 12 and then another batch and then halving all the ingredients and baking a batch of 6 cupcakes. But we can make it simpler and do it all in one go if we calculate the multiplier that will take us from 12 to 30. Fortunately, this is easy to calculate, as we can divide where we want to end up, 30, by where we started, 12. So 30 divided by 12 gives us 2.5. So our multiplier, or scale factor, is 2.5 for all of these ingredients. And if we multiply this by 2.5, we get 250 grams of butter, flour and sugar, 5 eggs and 50 grams of chocolate. Let's look at another way that proportion is used. In this question, we have 4 boxes of grass seed, where all the prices are proportionate to the size of the box. We have the size and the price of a 1 litre box, which is £12, and we're asked to calculate the prices of the other boxes. We can use the same process as we did with the recipe question in finding the scale factor. Let's find the scale factor from the 1 litre box. 12 divided by 1, which gives us 12. So for every litre of grass seed, the box will cost £12. It helps with starting with a base measurement of 1, as this makes the scale factor very easy to calculate. I can now multiply 2.5 times 12 to give us £30, which is the price of the 2.5 litre box. 7 times 12 will give us £84 for the 7 litre box. And now we can calculate this box, which is 0.75 litres. Remember that even though we're multiplying, if we do this by a number smaller than 1, the amount's going to reduce, as is the case in this point. 0.75 times 12 gives us £9. So now we've calculated all of these with the same scale factor, so we can say they are all proportionally the same prices. Let's look at how we can use a scale factor to both scale up and scale down in another example. Here we have a picture and a poster, which are similar shapes, and we're asked to find the height of the poster. As they are similar shapes, we can use a scale factor and calculate it from the bases of both the photo and the poster. As the poster has a base of 17.5 centimetres and the photo has a base of 5 centimetres, we can calculate it as 17.5 divided by 5 gives us 3.5. So we know the height will be 3.5 times larger on the poster than on the photo. So we can do 12.5 times 3.5 to get 43.75. Let's look at how we can use the same scale factor to scale something from the poster back to the photo. If we're told that the Eiffel Tower in the poster measures 35 centimetres, how do we use the scale factor to calculate the Eiffel Tower in the photo? We could create another scale factor. However, if we understand that the opposite of multiplication is division, we can continue to use the scale factor of 3.5. 35 divided by 3.5 equals 10. So we can state that the Eiffel Tower in the photo is 10 centimetres tall. Now, let's look at how the word similar is used with regards to proportionality. In this problem, we have 2 similar triangles and are told to calculate the area of the larger triangle, B. We can tell they are similar as all the angles are annotated as being the same within the context of this question. If the lengths of each of the sides were the same, we would state that the triangles are congruent rather than being similar, meaning they're identical in both size and shape. There are 2 ways we can complete this. In the first, we can calculate the missing side using the scale factor created by 8 divided by 4 equals 2. And then calculate the missing side perpendicular to 8 centimetres as 6 times 2 equals 12 centimetres. We can then calculate the area as base times height divided by 2, 12, times 8 divided by 2, which will give us 48 centimetres squared. However, we can use the same scale factor to calculate the area from shape A if we remember that the area is two-dimensional, and therefore the scale factor will have to be to the power of 2. As we will be multiplying both sides by 2, this should give us the same answer as the previous method. 4 times 6 divided by 2 gives us 12 centimetres squared, and then 12 times 2 to the power of 2 can also be written as 12 times 4, which gives us 48 centimetres squared. And we can see this is correct as we check it with the previous method. Now, let's look at how we can use that method with a volume. Here we have two similar cones, A and B. We're given the formula for the volume of the cone as volume equals 1/3 times pi times radius squared times height. Let's calculate the scale factor from the two known terms, the radii from both shapes. So the scale factor is going to equal 15 divided by 5, which gives us 3. Now let's calculate the volume of cone A, 1/3 times pi times 5 squared times 10. This gives us a volume of 250 over 3 pi. I'm not going to change that to a decimal yet on my calculator, as I want to keep the accuracy of the fraction for as long as possible. I multiply that volume by the scale factor cubed, as this is a volume. 250 over 3 pi times 3 cubed gives us 2250 pi. If I convert this to a decimal, I get 7068.58, which I can round to 7068.6 centimetres cubed. This is used in several questions that I've seen in papers from across the awarding bodies, and an understanding of scale factors makes a complex problem a lot simpler. In this video, we've looked at using a proportional multiplier to change the size of shapes and quantities. We've calculated the multiplier, or scale factor, by dividing the size we want by the size we know. With each increase in dimensions for the area or volume, we need to increase the power of the scale factor accordingly. As always, we made sure we're using the correct units of measurement with each question. In the next video, we'll be looking at calculating using direct and indirect proportion. I'll see you then.